Thank you. Thank you, Mr. Chairman, ladies and gentlemen. Yeah, my name is Timo Saarenketo, and I am a managing director of a company, Road Scanners. And I guess I'll introduce myself with a couple of next slides and a little bit about our company's history also. Basically, our presentation today is titled here. I don't know what is I'm supposed to speak, but I'm speaking today about mainly about GPI inspection on the asphalt dikes, and my co-author or partner on this presentation, Tommi Herronen, he is officer manager in Road Scanners in Finland, and he's been doing mainly the data processing. A little bit about Road Scanners. We are quite soon 12-year-old company. And before that, my history was that I was working almost 20 years on the Finnish National Road Administration for material testing and site investigation and NDT. A couple of years I have spent in USA, in Texas, doing also on my PhD on this issue, how you can detect material properties by using electromagnetic testing methods. And part of this technology is what we've been developed are based on that. So Road Scanners in general is a consulting company, but also is developing software and instruments for roads, railways, airports, and also for special investigation like dikes or we are also right now working on the nuclear waste disposal testing with very high demands on detecting different type of cracking. This is where we are mapped at the moment. Our head office is far north in Rovaniemi on the Arctic Circle. Then we have two field offices or brand offices in Finland, Tampere and Helsinki, daughter company in Sweden. And then we have in Europe 3 offices, one in Germany, taking care of German-speaking Europe and Africa, and then in Brora, Scotland, taking care of Ireland and UK. And in Tallinn, we are working mainly on instruments. On the right-hand side, you can see our operation countries this year. We are quite international company. Greatest part of our turnover comes from the exports, and we've been working and providing systems, different type of system. The last is quite exciting system that we just delivered to Antarctica, a warning system to cars that they don't crash to glaciers, through crevasses. They are now developing the first. You can have safaris in Antarctica, starting from a couple of months, driving cars, and there are major cracks in the glaciers, and we made a more warning system that these cars don't drive over there. Anyway, the special expertise what we have is ground penetrating radar technology. And for that we are providing service, software, training, and quite much turnkey system, which means that a company or organization wants a system, so we are building and training their technicians and providing also customizing software for them. One example here in the center is a forest enterprise in Scotland, and or in UK that is managing their road network in UK. Payment diagnostics is one of the key parameter what we've been working, and especially on the payment diagnostics it's not only GPR but the system integration. And the major thing is profilometer historical data with falling weight data, GPR data, which can be seen. And then you can calculate different type of historical parameters and make warning signs that this part of the road is deteriorating faster than predicted, and you should go, for instance, and check if the culvert is not working or what's the problem. And we can calculate the remaining lifetime. So that's part of the work. And for that type of work, we've been developing for different customer segments, different type of softwares, road doctors, railway doctors, geodoctors, and different type of modules. But about GPR, I guess part for you, GPR might not be so familiar, so I'll tell a little bit about technical background, how GPR works, and then you get better idea how we have been doing this dike inspection. GPR consists of antennas. They can be air-coupled or ground-coupled. And air-coupled antenna means that its antenna properties don't change while you are driving over the dike. And ground-coupled antenna is having a good penetration. It's very sensitive to cracks, but its properties are slightly changing if the dike properties is changing. So it's hard to get repeatable data using them. Then you have a control unit controlling the systems, power supplies, videos, GPS, encoders. You might have a drilling system. And the system works that with the transmitter, there are two antennas in these boxes normally. Transmitter antenna sends a signal, electromagnetic pulse to the pavement or asphalt, and part of that energy, when it meets the surface, is reflected back, and part of that energy is penetrating deeper. And each electrical interfaces, part of the energy is reflected back and going deeper and deeper until the signal is attenuated so much that you cannot anymore record any reflection. And from that we are measuring normally this amplitude, and also the travel time. So the travel time, two-way travel time from the asphalt surface to asphalt bottom. From that you can calculate then the thickness of this layer. And the travel is how fast the signal travels in each layer is then it's detected by its material properties. And once you repeat this on kilohertz frequencies, and you are driving, so you can get a continuous profile over the material or over the target what you are wanting to inspect. In this work, where we've been doing is, normally when you are getting GPR data, you are seeing time, everything is so-called time domain. So amplitude is plotted against time. And from that you can calculate the thicknesses. But once you are starting to do material properties, testing material properties, then you have to analyze also this amplitude versus frequency, what you are calling frequency domain. Because it's not as one single frequency what you are measuring and transmitting from these antennas, but pulse radar antennas, but several frequencies, and then you have to calculate this bandwidth. The properties of the material that are affecting to the signal. We are mainly having two properties, or three properties: magnetic susceptibility, electrical conductivity, and dielectric value. Magnetic, we can ignore that. We don't have so much magnetic components in asphalt or road materials that it doesn't affect. But the two last ones, especially on dikes, are important. Electrical conductivity, because you have a salty water through the splashes and the foam from the sea, and that affects, and that's causing signal attenuation. And then you have a dielectric value that is caused, and that's affected by the compaction degree of the asphalt, and then how much water you have in the pores of asphalt. That they are the mainly. So conductivity and dielectrics, this is a list. I don't go very detailed through that, but this presentation is stored in this seminar database. Those you want to see that, but mainly porosity of the asphalt, volumetric water content, water distribution, how much is there free water, and not the bound water, and ion concentration. So how much there is water salt in the pores. These are affecting both conductivity and dielectricity. And why we can measure on these minor problems in the asphalt is that when you are putting different frequencies, so you can have a conductivity or electrical conductivity and dielectricity, and then when you are putting frequency over there, so you can they are changing, they are frequency dependent, and this is based on what type of polarization happens in over there. And when you are using GPR, you are working on basically on this frequency area, where you have a molecular polarization, which means water molecules react your electromagnetic signals, but then you are starting to reach also ionic polarization, which means that it's very sensitive also on the chloride content and damages. And by calculating ratios and complex frequencies from both of these, then you can define what type of material, what is the material properties of this asphalt and how they affect. So this might sound quite complex, but basically this is the same process that you see colors in the visual light. Colors are forming from the walls or wherever that some part of the reflection, it affects to the frequency components of your signals, and this is basically in a way simplified way what we are doing. Then we still have to keep in mind that asphalt are composite material. We have a bitumen, we have aggregates, and we might have some filler, and we have air, and later on the asphalt we have also water there. So all these affect the final form of an electromagnetic properties, and how they interact also between these components. So basically, if your bitumen aggregate bond breaks down, that forms immediately some neutrons are given away, and over there you can see changes in the frequency response. This is just one example of my work, what I did in Texas Transportation Institute with different type of material properties on the asphalts and aggregates, the real parts which is affecting the signal velocity, and the imaginary parts which are affecting then the attenuation parameters. And I did also some testing of bitumen, aging of bitumen, and according to this test, that the aging of bitumen doesn't affect. So that is one good news also for GPR. Always you get from the exact bitumen itself, you get the same response. Then one thing about the maps and presentation later, what I'll tell is that once you are doing different frequency, you have to keep in mind also that you are measuring different depths, because the wavelength in higher frequency is shorter than the lower frequencies. And these antennas, 1 gigahertz antenna and 2.2 gigahertz antennas, means basically that most of the energy you are not getting from the asphalt surface in 1 gigahertz is about 35 millimeters. But in general, you get up to 40 to 50 millimeters. But in 2 gigahertz, you are measuring only first 20 millimeter layer. And so it's a thinner slice from the surface on the material properties. What you can do with there, so on asphalt quality control, you can calculate air voids content, and that's a standard method for asphalt contract, has been more than 10 years in Finland. It's a routine. USA has started also work for that. We are in the Sharp 2 project to get air voids content compaction method for asphalt. Then you can calculate moisture in old asphalt pavements. You can calculate pavement distress, what I will show today. And then you can get like a pavement roughness, what we are calling poor man's IRI. Some of you, it's called International Roughness Index. It's a simplified way to get information on that. But let's go to the dikes and experience on these dike surveys. First, we started this test in 2007, did a couple of testing, one in Friesland and one in Hellegaards Dam, and we were using Norwegian step frequency 3D radar and American GSSI air-coupled radar. This is slightly different. This is pulse radar, and this is step frequency radar. We thought that this might give even better results because you very precisely can control the frequency response. But the problem was that we couldn't get enough good quality data. There were some problems on the mechanical design of these antennas, especially when it's in a very wide angle in these surveys, and we couldn't control the coupling effect, and that is why we didn't get good data. And I have in this presentation, I pretty much skip this data and focus mainly on the pulse radar data. So first data, what we analyzed, we got the thickness of the asphalt, and then we calculated this kind of contour maps and dielectric values. Dielectric value here, blue ones are pretty much 4 to 5 to 6, and red ones are then close to 8 or 9, which means that it's already absorbing quite much water, and there are indications also of salt. These are individual survey line parameters. So on the dike we are doing several passes, and then we can, from that results, we can make such a contour map. So where there's a time 0 and there's 12. And once we compared, Koak and Arjan took the reference sample, and when we compared the reference sample with our map, so we got pretty good match of the known problem areas and the samples, and that encouraged to continue the test. And in 2008, last year, we did the test in near Jacobi Parocci dike, and that was a little bit more extensive testing. We still use 3D radar and GSSI radar. Now we try to lift the 3D radar up to avoid these coupling problems. Still didn't get too good results, but the pulse radar results were even more encouraging. We got also digital videos. And in this data collection, we used 36 lines, half-meter spacing, and we took 20 scans per meter, which means about 5 centimeter spacing. And once the step area is about 30 centimeter by 30 centimeters, so we are getting like 4 to 6 scans from each area, and so it covers the whole area. And the results from these 2 antennas you can see here. You can see asphalt. Beneath that you can see aggregates. Here about 20 to 30 centimeter layer. You can see here, and then the soil fill, whatever it is there, is beneath that. But in this work we focused and concentrated mainly on the asphalt and bituminous layers. Depth is presented here. What we see that there were quite big changes on the depth. So the depth is starting from 200 to roughly 300 millimeter, a little bit more than 300 millimeter were the biggest part. Then we calculate, I already mentioned that we were talking about poor man's IRI, so we could calculate, and we can measure also the evenness of the asphalt. And that means that we are measuring due to the height calibration, we are measuring very accurate distance from the antenna to the asphalt surface. And now when the car is bouncing, so that distance is changing. And that you can make also a map, and we are calling that antenna bouncing map. And this explains also a little bit on that, and about the surface properties. And especially in this place it was quite interesting that even though we had 32 lines, and when we made the map, so you get this wavy form. So it's not even totally, the surface wasn't too even on these sections. And then we calculate the asphalt dielectric value, and and this data map is from the 1 gigahertz horn antenna, the lower frequency part. And now we got pretty good match on the drill cores, and even more encouraging was the results what we got from the coax when they opened and sent the damages. They matched it quite well on these areas. It's only, I think the problem was that over there the field survey crew couldn't find any problems, even though it was a little bit visual also, that damage was in visual on that side, but it wasn't mapped over there. Then we compared, very interesting result was when we compared the thinner slice. So this is the 2 gigahertz antenna. So with that you could find only some areas over there. And what does that mean? That means in general that your damages start a little bit deeper than the surface. It's not on the first, they appear something like 30 to 60 millimeter down on the, and then they start to come up. So the damages don't, so this is a clear indication on that based on our other surveys. Also, what we did basically in this map also, that we compared, we subtracted the dielectric value from here, the lower antennas, and that was also interesting map that we showed that it seems to be that the early phase damages are starting to appear also in this wavy form. So this how the damage pawn seems to be related on the small longitudinal waveness on changes on this asphalt dike. And that that can be confirmed when you are comparing this calculation map, dielectric map from 2 and 1 gigahertz antenna with the antenna bouncing map. And you might claim this, detect that the calibration is not correct, but the calibration is extremely well done. We checked that, and we know that worked well. So this is not a calibration issue. It's an issue where you can it really exists on that side. And here you can compare the existing maps also, and you can see that the biggest or the visual damages were mainly on those areas where there were biggest differences also. And here is a photo from that side, and you can see a photo from here taken from our video camera still photo. So clear indication also on the surface. Then a little bit going back from the dikes to roads, just one example then how we are calculating these parameters also on the roads. This is one of the latest work what we have been doing in M5 motorway in Hungary, where there were major problems mainly on lane K1 where the heavy traffic was using slightly newly rehabilitated road. And this is how we did the work. So this is the surface map what I showed also, the dikes. And now you can see also the load effect. So heavy trucks are using that, and you can see the wheel paths here. The same area. This is where the Hungarian crew have found different type of cracking. And that cracking can be related that now also the loads are starting to do the related problems. This moisture content is calculated inside the asphalt. And you can see that in this area with the problem there is quite much excess moisture also inside the asphalt, and that is causing problems. The third map is beneath the asphalt. So over there you see that there is not, like the base cause cannot be blamed, but it's coming somewhere else, the moisture. And the fourth map is the thickness, and you can see compare if these damages can be related to thickness. Then when we analyzed that data, we came and started to remember that we have had analog damages in roads also. And that these damages can be explained as like thermodynamics, using thermodynamical theory, and especially on suction theory. And a little bit about suction. Suction is the force causing negative pore water pressure in the material. And it is caused mainly by total suction and crude suction. They are the main component. Total suction works when the ground is non-frozen, like right now here in the Netherlands. And that is composed mainly by two parts: osmotic suction, osmotic forces, and that's caused by chlorides, how much you have chlorides in the pore water, and matrix suction. That matrix suction is mainly on the void side of the voids, if you have fines in the void in unbound materials, and that is that causes how much water is absorbing over there. And crude suction starts to affect when the air temperature goes beneath 0, and its biggest crude suction is biggest between -0.5 to -1 degrees, when part of the water is frozen and part is unfrozen. This is from Texas one test results about two types of aggregates. When they are unfrozen, their suction value, this has high fines, it absorbs more the water. But when they are frozen, their pore water pressure is about 100 up to 800 times higher. So when material freezes, it really starts, makes a really strong force to suck the water, absorb the water from the surroundings. And that's the key element of that. In roads, we have been using this theory for years already. And this, for instance, this is from Scotland. This is the freeze-thaw cycles in Scotland, and here you see the dielectric value of unbound base under the road. And from the measurement station, and always when you have a freeze-frost areas followed by rain, you get high moisture content on the base core. And we know that if unbound material base is more than 16, you will have problems with the permanent deformation and failures on the road. But we are now talking about dikes, so we don't have the load effect. So it has to be something else. And this is a example of the road what we did in survey in 1998. This road, this is a brand new motorway, opened 2 weeks after opening, and they had to put a speed limit of 50 km per hour because of these bumps on the asphalt. And like a major, you can imagine, major catastrophe for the road owners, and quite embarrassing thing. And we did a quite detailed survey, found out that the reason was extensive de-icing extensive use of de-icing salt. I don't show too much details on that, but a little bit more about similar effect in Finland. In couple of years later, 2001, we had similar thing. Brand new motorway opened, and 3 months after, you had like so rough road that you thought that you will lose your teeth fillings when you're driving 80 km per hour because it was so high washboarding over there. And we did this survey. This was on the winter time when we drilled the core from the asphalt, and here you can see the core. And this area, again, about starting from 40 centimeter to 90 centimeter, these are filled with ice. So you get ice lenses over there. Also about big layer, not in the surface, but slightly deeper, like in your dikes. And that was the reason on this top of these bumps. And once they were thawed, the asphalt was totally cracked on this area. So the damage process, what we have been proposing on this kind of areas is that you have this type of blade spreading systems in the salt, in the new asphalts, and that is not totally evenly spreading the salt in the first area. So you get some concentrations, and also the pavement is not totally smooth. And now the salty areas start to absorb more water through the osmotic suction. And then when the temperature goes beneath the 0, so these areas where there is not so much salt, they freeze first. It's about 0.3, 0.5 degrees lower. And now when I showed you the cryosuction things, now these are frozen, these are non-frozen. So these form cryosuction forces. Negative pole for the pressure about 800 times higher than anywhere else. And that is causing that water starts to flow from these more salty areas to lower salty areas, and are forming ice crystals. And then you see this effect, what you saw in the drill course. It starts to push up, and then you see, not in the surface, but slightly deeper here, you start to see these damages. And in worst areas, they are forming cracks, and then they got even more water. But later, if the winter continues, they get a little bit more even, because then the salty areas also get frozen. But here in Netherlands, you get hardly ever minus 20 degrees that temperatures like that this would happen. So you are talking mainly on this effect here. So what our idea is that now the water from the sea comes and splashes the areas and the salty water, because it's not totally even, so it spreads to certain areas and they get the more salty water than these upper hill areas, and that causing, because the change of the asphalt looks like that, and that can explain the damages. Then about distresses. Distresses is used for asphalt and how you calculate and how you make map. So that dielectric value map was one good way to show the material problems. Other is that the problem anyway with the dielectric value is that it shows the moisture content, but it shows also the absolute dielectric value is if you change the aggregate type, if your asphalt mixture is slightly different, so you get slightly different values. And if you are detecting only voids or cracks, then you can calculate deviation of the dielectric value. So in the areas where you have cracks in the pavement, the deviation is very high. And in areas where you have a smooth pavement, your deviation is very small. So once you go and not measuring the absolute dielectric value, but you are measuring the deviation, and once you are making deviation maps, we tested here also, and they provided excellent, even better results to match with the existing problems than the absolute dielectric values. So that was a very promising technique, seems to be working also on the dikes. Then one thing what we didn't too much focus and concentrate is that with GPR you can scale also the moisture content under the dike. And this is the dielectric value map under the asphalt, not under the asphalt. And that shows that you have certain areas higher concentration of moisture. Of course, when you are talking about asphalt dikes where you don't have a dynamic loading, so you don't have so much permanent deformation risk, but anyway, if you are looking some leaking or if there is a risk for washouts or anything similar on the asphalt covered dike, you can use dielectric values to survey on that. Finally, one interesting thing what we found also on that dike was that once we analyzed that on the 3D software, so this is a one longitudinal line out of these 32 lines. This is the cross section, and this is the one time slice taken inside to the asphalt. And what was interesting and paid our attention is that you start to see these kind of features evenly spaced, like a crack type of feature. This is from this area, and you see like about 4 or 5 meter spacing of these cracks. And that reminds me, I'm not expert how to lay asphalt on the dikes, but seems to be that they've been placing this on this spacing. And what was interesting also, that once you made the longitudinal map, wave map, and compared this spacing, they seem to be similar wavelength. So this unevenness could be related somehow how the work was done, and I don't know if the paving was going up, down, or what was the reason, but this is definitely not imagination. GPR cannot lie, so it measures just some parameters, and this kind of parameters could be found over there. Then especially on concrete roads, we are using frequency parameters to calculate moisture content. And especially on concrete asphalt roads, that is the best match on the existing damage and if there is moisture content. We have tested that But results have given that this dielectric and dielectric dispersion maps are much better and match much well with the known problems. Finally, a couple of new slides of the latest test, what has been done in Eemshaven dike survey a few months ago. And here we repeated basically the same surveys with GSSI horn antennas, but now we tested also the new Italian IDS system, which is 1 meter wide antenna with 10 centimeter spacing antennas. This is mainly for bridge decks and concrete roads, but we wanted to test on this project also how well it works on this kind of dikes. This is preliminary results. These haven't been published yet, but just wanted to show a couple of nice examples how it shows. This is the 20 meter wide area and 100 meters. So here you see the first area with the problems, and in that area you can definitely see also in the surface some features also of the deterioration. Going to the next 100 meter, some areas, and continuing, still certain areas seems to be also concentrating on the high dielectric values to certain areas, especially on this area from 2 to 8 meters from the sea level. And again, map from 300 to 400 meter. But then it was an interesting area. From 400 to 440 meter, totally blank, low frequency, no deviation. And once you look at the asphalt, so it was a new, I guess it was already fixed, and that seems to be quite well matching also that this is a new asphalt with no problems, and you can really from that data you can see that this makes sense, that you can get early phase damages already. Once you get the homogeneous dielectric matching or dielectric electrical response, that means that the asphalt doesn't have any problems. There are a few lines showing the same feature. So this area with no deviation, homogeneous, can be seen in this section. Here is, we compared also the dielectric deviation maps. We don't have any yet drill core or any reference data from that side, so we don't know how well it matches. But we can see some of this wavy deviation here, but in this area it's not so clear. So looks like that the reason for the damages could be slightly different on the Eemshaven, and we couldn't see this cracks in the spacing. But again, antenna bouncing, that was antenna bouncing map is here. It's very even, and also dielectric deviation is very small in area. In that area, that was a good quality. So finally, conclusions what this test for the last 3 years has been that it's they have really shown that the GPR is a useful tool for detecting damages in the asphalt. It works in road, it works in dikes. And GPR data indicates that asphalt damages can be related to salt and freeze-thaw damages, and similar damages have been found in roads in Scandinavia. Similar cases have been also in Canada. There is in Quebec some excellent cases also available. And so far we have got the best results using horn antennas and GSSI horn antennas, and especially the 1 gigahertz seems to be the optimum frequency to get these damages that are slightly beneath the surface. The higher frequency seems to be taking too thin slides on the top. You have to go a little bit deeper, use longer wavelength. The maps on this monitoring dielectric value of asphalt surface seems to be excellent. Dielectric deviation can be even better. Antenna bouncing map shows a little bit about the surface properties, mechanical properties, and if you're interested on the base course or unbound material beneath, the dielectric of pavement bottom could be also good. And finally, what we think that this technique could be now ready for production phase. So we've been testing so much, get unique results that make sense, and in that way, for my experience, this could be started like a monitoring this asphalt and getting early phase damages, even like preventative maintenance, but also mapping the areas where there are damages, and you can only fix these problem areas, and you don't have to replace asphalt the whole pavement. So I would say that at least my idea and understanding is that like a production part on the routine surveys, this is so convincing that I could like recommend this work. So thank you for your attention.
Timo, thank you for this excellent presentation. Very interesting. I would like to open the floor for questions. Okay. Are there questions? Come on, guys.
I was just wondering, in the maps that you show us,
yes.
What kind of interpolation technique do you use? Because I got the feeling that you have to combine the lines of survey to get a complete map.
Yes, yeah.
Correct?
Yeah, there are several interpolation techniques. To be honest, we are using Road Doctor software, and it can use like a linear regression, or what do you call this, step by step, or the.
What I noticed in one of the slides, maybe we can go back a bit more. There's one like a survey line that you might detect. Well, that one maybe. There. You see, if you look at the bottom one,
yes.
You have a red line at the right-hand side.
This one. Here.
You see a survey line over in this direction.
This
yes,
one. Yeah,
one.
yeah.
Is that a survey line? Where the
yeah,
actual car has been driving? Or
that is part of the survey line, and we were thinking first that it's a survey line. We were thinking on the last meeting here also. We were looking at the videos, but exactly on that place you can see a small bump, and you can see a defect over there.
Okay. It's not an
no,
effect of
we were thinking.
So.
Yeah, we were thinking also that it could be like some kind of a false calibration, especially on that one line. But we could see a damage on these areas, especially on that area. I don't have a video with me, but that.
But it's very interesting also to see that you make the connection between, like, the salt problem in Scandinavia regarding to using asphalt in salty areas for protecting
yes.
dikes. It's good to have that possibility to compare those different results and know what kind of underlying problem might be the cause of the actual image that you're seeing.
Yes.
Yes.
Thank you.
That's very interesting indeed. Are there more questions to add to this? because that comparing with each other, I think that's an important thing. I have also a question, because it's very interesting to see that antenna bouncing parameter, because that's giving information, in fact, on the unevenness.
Yes, it's
and so the areas where you can collect maybe salt from seawater, etc., that could be detected in that way.
Yeah, exactly. Because it is like there's what we know also from the roads, that then the salt water is concentrating over there and it stays there and evaporates probably on certain areas. So we did, I didn't show, but we did one map also about amplitude analysis. And in the first or second report was that so you can see that.
Yeah. So it means, in fact, I've never cared about evenness on a dike in the past, but maybe now we should think about putting effort indeed in getting more smooth dike surface to not have too much of these undulations, in fact. That's the message, I see. Yeah. There is another question coming up, I think.
My name is Harmen Faber, Rijkswaterstaat IJsselmeergebied. Your presentation on this salt-related bubbling of the asphalt, you found this in the dikes in the Friesland.
Yes.
I've also seen the dike. And that remembers me to a dike which I'm involved with, the Houtriberdijk. That's a dike in the middle of Holland, between two parts of fresh water in the middle of the Lake IJsselmeer. It's fresh water on both sides, but with a road on top. And on the road they use salt in winter time. And we see bubbling of the asphaltic dike pavement more in the neighborhood of the top of the dike, in the neighborhood of the road, than in the bottom. That's what I remember. So maybe, that is one way what I remember, which might have gives. Maybe it helps with more research here in the Netherlands.
Thank you, Harmen, for that.
Excellent notice. Yes.
Yeah. Okay. Are there more questions? Or are we getting hungry for lunch? Timo, I would like to thank you, and I think we should applaud him for this very excellent presentation.
Thank you.
And now it's time for lunch, and I would like to have you back. En nu is het tijd voor lunch. En ik zou jullie graag rond 1 uur weer terug hebben hier. Dank u wel.